Okay, remember from, I believe it was Tuesday, we started talking about section 2.3, which is about Newton's second law. And remember that Newton's second law states that when an unbalanced force is applied to a mass, the mass accelerates, and it can accelerate negatively or positively. Another way of looking at this is that acceleration depends on two variables, and that is the net force being applied to the object and the mass of the object. All right. Then remember we looked at these two scenarios, and they were basically Newton's first law, which was on this side, as opposed to Newton's second law, which was on this side. Remember that in the first law, we said that forces are balanced, and that means that acceleration equals 0. So I'm going to be going over, I'm just doing a brief review of what we talked about on Tuesday, and this was one, and then I'm going to go over the homework from Tuesday as well, and this was one of the questions, the first question, I think, from the homework. So remember, Newton's first law states that an object will stay in motion as long as, or it will stay in motion with the exact same velocity, meaning velocity doesn't change, unless an unbalanced force acts upon it, or it will stay at rest. And that's what these two situations are, right? So an object could stay at rest, meaning its velocity is 0 meters per second, and it won't move, right? It will stay at rest until an unbalanced force is acting upon it. And the other situation, an object will stay in motion, velocity will be constant unless the object is acted upon by an unbalanced force. That is different from Newton's second law that says that when we have acceleration, or when a force is unbalanced, that means that acceleration is occurring when there's a force being applied to the mass or the object. So when the forces are unbalanced, there is acceleration. It can be positive or negative, and it depends on the net force and the mass of the object. Then remember we looked at the relationship between net force and acceleration, and we said that net force and acceleration are directly proportional. And then we looked at mass and acceleration. Force and acceleration are directly proportional. Remember, that means that as force increases, so does acceleration. As we increase the force applied to an object, acceleration increases. As we decrease the force applied to an object, acceleration decreases. We slow down. But in either case, acceleration is occurring. Whether acceleration is going up or going down, it doesn't matter. We still call that acceleration. Acceleration is still occurring. All right, then we looked at the relationship between mass and acceleration, and remember that we said mass and acceleration are inversely proportional, and we used this example of the ping pong ball and the yoga ball, and we said that when the mass is decreased, the acceleration increases. So as one goes down, the other goes up, or alternatively, as mass increases, acceleration goes down. So there's an inverse relationship here between mass and acceleration. And from these two ideas, relationships that we saw before, that we studied before, we came up with this equation. A equals acceleration equals the net force, so it's directly proportional to the net force, and it's inversely proportional because we're dividing and mass is on the bottom here, inversely proportional to the mass. So this was just the equation that we used to basically put into math what we were looking at, the relationships we were looking at before. And remember, I said that it's often this equation, this is the equation for Newton's second law, but usually it's usually it's written like this. You'll usually see it like this, but that's just this rearranged, okay? It's just usually written like this because that's just it's nicer to look at, it's easier to remember, okay? But when we rearrange it for A, we get acceleration equals net force divided by mass. All right, then we looked at some different examples of how net force changes as acceleration increases or as mass increases or decreases. We looked at those relationships. Okay, let's now look at the 4 homework problems that we had for 2.3a. So for number 1, I was basically wanting you to give me this, to go over this, these 2 scenarios with the arrows, the kind of spider web things. I don't remember what those are called. Web diagrams that we did in class. I wanted you to, where'd you go? There you are. Go over, basically just go over those, compare and contrast Newton's first laws. If you did the diagram, then you got full points. If you explained it in words, that's fine too. Okay, so again, type of net force for Newton's first laws, it's going to be balanced, right? Because we either have no motion, we're at rest, meaning the velocity is 0, or we have, go back. So we have the object at rest, velocity is 0, or we have a constant velocity. In either case, the acceleration will be 0. It will not be accelerating, right? And the net forces in both of these situations are balanced, okay? And then for Newton's second law, I wanted you to talk about how the net forces are unbalanced, and there is acceleration, which is negative or positive, and that acceleration depends on the net force and the mass of the object. Okay, so something along those lines for number 1 would have been great. Then for number 2, it says a 15 Newton net force is applied first to a 5 kilogram object and then to a 10 kilogram object. Estimate what will occur to the acceleration in both situations described with the different masses. So we're going to have 15 newtons of force being applied. Let's say that this is a 15 Newton force being applied to a, this is 5 kilograms, and then we'll have the same thing, 15 newtons of force, but being applied to 10 kilograms. So what I wanted you to understand here, or to explain here, is that since acceleration depends on net force and mass, as we increase the mass, we're increasing the mass here, right? There's an inverse relationship between acceleration and mass. Inverse relationship. So that means as mass increases, but we're not changing net force, right? It's the same in both situations. We're not changing net force, but we are changing the mass. So we have a low mass here, meaning we would have a higher acceleration. And we have a higher mass, bigger mass, larger mass, down here in the second scenario, but we would have a lower acceleration because there's an inverse relationship, between these two. Okay, so if you did it mathematically, we could have done it mathematically to prove in this. We would say acceleration equals 15 newtons divided by 5 kilograms, and that's going to be 3 meters per second squared. Or we could have done down here 15 newtons divided by 10 kilograms, and that's going to be 1.5 meters per second squared. So you could have done it mathematically if you wanted to, and then compared them. It does make sense. What I said without doing it mathematically, our inverse relationship does hold true. Here we have the smaller mass, so we have the larger acceleration. And here we have the larger mass and therefore the smaller acceleration. We can see this inverse relationship right there. All right. Letter B wanted you to determine, oh, there you go. Well, we just did that. Letter B wanted you to determine mathematically the acceleration in both situations. So it was 3 in the smaller mass. That was a horrible square around that. 3 in the smaller mass and 1.5 in the larger mass. And then C, what type of relationship exists between acceleration and mass? That would be an inverse relationship or an inversely proportional relationship? Either one of those answers would have been stellar. Okay, now number 3. So we have a 5 kilogram object. A 5 kilogram object first has a 15 Newton force applied to it, then it has a 30 Newton force applied to it. So let's first draw our diagram. We have a 5 kilogram object with a 15 Newton force being applied to it in the first scenario. Second scenario, we have a 30 Newton force, right? Yes, being applied to that same 5 kilogram object. Okay, so there's just what we're looking at. Estimate what will occur to the acceleration in both situations described with the different net forces. Well, we're not changing the mass, and we're just looking here. So we're looking here at the relationship between force and acceleration. So here we have a small force. So since we know that there's a directly proportional relationship between force and acceleration. Remember that? Directly proportional. Yes. So that means that as one goes down, the other goes down as well. So we have a small force here, 15 newtons, small compared to the 30 newtons. Then we would have a small acceleration, and the opposite would be true in our second scenario. We increase our force, therefore we increase our acceleration. B wants us to determine this mathematically. So if we do that, we have acceleration equals 15 newtons divided by 5 kilograms. Again, that's going to be 3 meters per second squared. And then down here, for our second scenario, we have acceleration equals 30 newtons divided by 5 kilograms. So here we have doubled our force, and therefore we have doubled our acceleration. So as I said, if you look here, we have oops, that's the mass. We have a small force, therefore we have a small acceleration. Here we have a large force, so there we have a large acceleration. And if you look at it directly proportionally, we have doubled our force, right? We exactly doubled it. 15 to 30 is a double. We do the same exact thing with our acceleration. So we did times 2 for our force, we do times 2 for our acceleration as well, right? So this shows us our directly proportional relationship, which is our answer for part C. What type of relationship exists between acceleration and net force? All right, number 4. Number 4. A force of 22 newtons is exerted onto a large textbook that causes the book to accelerate at a rate of 5 meters per second squared. First part, draw a free body diagram of the book. So I didn't give you right or left, so whatever you put is fine. We have an applied force of 22 newtons. We have a normal force, and I just wrote G, sorry. Normal force, and we have a force of gravity. I didn't tell you the mass of the book, but we would also have friction force here, but we don't know. I didn't give you anything about the net force on the book, so did I give you anything? Oh, I did say net force on the book. Okay, so then we can just erase this. This is the applied force, but it's the net force, so we'll just leave it as that. And it is, if you wanted to draw a friction force, you could, but this would be the net force diagram, right? Because there is friction there, but because I said it's the net force, we are not going to draw the friction in there for right now. Okay, so what is the mass of the book? So our knowns, unknowns, and equation. We know that our net force is 22 newtons. We know that our acceleration is 5 meters per second squared. What we're looking for is mass. Our equation is F equals A, or A equals F divided by M, whatever one you have remembered is fine. We need to rearrange this by dividing both sides by A. When we do that, we have mass equals net force, sorry, I forgot to write net there, divided by acceleration, and now we can solve. So we have mass equals 22 newtons divided by 5 meters per second squared. That gives us a mass of the textbook of 4.4 kilograms. That is our answer for part B here. And then part C says, what would occur to the acceleration of the book if the mass were tripled? And we assume the net force stays the same. So now, instead of having this 22 Newton force applied to the 4.4 kilogram mass, we're going to have a times 3 would be 66 Newton force applied to this same mass. So before we had, I'll just redraw them. Before we have a small mass, therefore we have a large acceleration. But afterwards, we're going to have a 4.4 kilogram book, but it's going to have 3 times the force applied to it. Whoops, I did mass in Excel, sorry. No, were we tripling mass or acceleration, or force, sorry? Oh, the book's mass, yeah, I'm writing that wrong. The book's mass were tripled, okay. Sorry, I've drawn that wrong. So we're not actually tripling the mass, tripling the force, we're tripling the mass. So we're going to multiply 4.4 times 3, and we'll see that the mass will be 13.2 kilograms, but the force stays the same. Okay, so now let's think about it. So here we have a small mass, I was right, and there we have a large acceleration because it's an inverse relationship, but in the second scenario we have a very large, or 3 times as large mass, times 3, right? So that means that we will have a smaller acceleration, and how much smaller will it be? It will be 3 times smaller. The acceleration will be 3 times smaller. So let's look, go back up here, I need to erase my stuff. Okay, so our acceleration will be 3 times smaller in the blue scenario, in the second scenario here, than it would in the first one. And if we want to look at that and prove that mathematically, we can do that. 22 newtons divided by 4.4 kilograms is going to give us an acceleration of 5, like we were given in the problem. So what, if you had to estimate what the acceleration for the second scenario would be, before doing the math, what would you assume that it would be? Well, we're increasing the mass by 3 times. So if we divided 5 by 3, maybe we would get the same thing, right? Because we're also decreasing the acceleration by 3 times. This would be 1.67 meters per second, so squared. So let's plug that in and see, or let's plug all of our information down here and see if that's right. So we have 22 newtons, same force, divided by our tripled mass. If we plug that into a calculator, we see that we get 1.67 meters per second squared, which is 3 times smaller than 5, right? So exactly inverse relationship. We increase the mass by 3, then we decrease the acceleration times 3 as well. Okay, and finally, the last part, letter D here, says what would occur to the acceleration of the book if the net force of the book were 1.5 times as strong as the initial net force exerted of 22. And we assume that the mass isn't going to change. So we have a 4.4 kilogram book getting a 22 Newton net force applied to it in our first scenario. In our second scenario, we're going to have the same 4.4 kilogram mass, but now we're going to triple the force. So here we have a small force. We will have a small acceleration. Here we're going to, oh, sorry, it's not tripled, it's 1.5, isn't it? So 22 times 1.5 would just be, would be 33. So here we're going to have a 33 Newton force because we're multiplying that force by 1.5 times. All right, so here we're going to have a larger force, a 1.5 times larger force. So that means we're going to have maybe a 1.5 times larger acceleration. If you want to prove this mathematically, so that the correct answer, if you didn't prove it mathematically, would be that the acceleration in the second scenario would increase by 1.5 times. And if you wanted to prove it mathematically, we could do that. 22 newtons divided by 4.4 kilograms, again, is 5 meters per second squared. Then for our second scenario, we have 33 newtons divided by 4.4 kilograms. And if you plug that into the calculator, you get 7.5 meters per second squared. And to double check that that makes sense, 5 times 1.5 is 7.5. So woohoo! Our math matches our logic. Okay. Alright, so we're done with that part. We will go over the next section on Monday. What I would like you to do for the rest of the period is, if you have any questions, please, about this, please send me a text or an email. Email now, I guess, since you probably don't have your phone. Send me an email asking me your questions, and I'll get back to you. And otherwise, you can start going over the last two sections of 2.3. We have 2.3C and D, which you can read either together or individually and take notes on, and those notes need to be submitted before the start of class Monday, but if you hand them in before this afternoon at 4 p.m., I'll give you an extra credit point on that assignment. So, okay, thank you. Have a good weekend. Please let me know if you have any questions.